Hi, and welcome to part 3 of this presentation on contact modeling using SOLIDWORKS simulation. My name is Ramesh Lakshmipathy, and I'm a senior technical sales specialist with Dassault Systems SOLIDWORKS Corporation. Let's get started.
All right, so let's talk about contact options. So far we've been talking about some of the mathematical options like node to node, node to surface, and surface to surface. What are these really, and how do they actually work behind the scenes? So node to node is actually what we call as a two-node gap element, and it really requires a lot of rules revolving around it. So, for example, it might require the surfaces to touch initially, and the surfaces should be relatively flat and parallel, and they can lift off during deformation, but they cannot slide with respect to each other. So what this does is it actually forces an identical mesh on both surfaces to line up the nodes between the source and the target geometry selections, as you can see here. The problem with this is it's the direction of the normal contact force and the points of contact are known in advance and remain unchanged throughout the analysis. So there is a one-to-one correspondence between the node on one face to the node on the corresponding or the other face. So in order to have that one-to-one correspondence, it, that's why the program ends up forcing an identical mesh on both the geometric entities. Now, another requirement of using node to node is the applied force should be parallel to the contact normal force or pressure. So what that means is if you have a force from going from one body to the other body in tension or compression, node to node might actually work great. And otherwise, if you had end up having some sort of a shear loading between the two faces, the node-to-node formulation might still work, but the results might be unrealistic. So again, the limitation really comes in when you have any kind of bending load or shear loads in your system, which is typical of many engineering applications, right? Uh, so most likely, I know the usage of node to node might be just limited in scenarios where you are dealing with a real life, practical engineering application of your product. So again, keep in mind that it's again a very simple formulation. It works really fast. It solves really fast. But again, depending upon what kind of loading is happening between two uh, bodies of interest, I should pay attention to that. And if there's any suspicion of bending or shear loads in your system, stay away from using node-to-node contact. Now, node to surface is a more advanced form of contact. It practically eliminates the limitations of the node to node mathematical formulation. So it's actually a one node gap element where you have the gap elements attached to the nodes in the source and the element faces on the target as shown here. The contact entities, the geometric entities participating in this type of contact, they do not have to be touching initially. They can have a gap initially. Later on, they can come and touch each other and physically interact with each other. They can move away from each other and all those things. So real advantage is surfaces can touch or have a gap initially. There's no need for a compatible mesh, and the contact location forces the direction are automatically determined and updated during the deformation process. So unlike the node to node where you have a predefined normal between the nodes one to one, which are corresponding one to one between the two surfaces of interest, uh, there's no need for that type of scenario here when you're using node to surface contact condition. Surface to surface is probably the most advanced. It's more for more complex loading, more complex physics, complex contacts. It actually does a fantastic job of converging much faster compared to node to surface. It does actually have to iterate a lot more because there are multiple constraint equations used between the two geometric entities participating in the contact, and hence it takes a little bit longer to solve. but it's more general than node to node and node to surface. It's really suitable for complex contacts with generalized loading, and it uses a more intensive, more robust contact algorithm. And however, it's not recommended when the area of contact between a source face and target face becomes too small or reduces to a line or a point during deformation. So sometimes you probably have a small step in your geometry, like 0.1 millimeter, that might be actually getting crushed like crazy. And again, you don't want to use this type of the surface to surface mathematical formulation in those scenarios. The node to surface actually works a lot more better in those situations. So in summary, here is a quick recap of node to node, node to surface, and surface to surface. So in terms of speed, general usage, accuracy, and robustness, you can see that surface to surface does the best job of all of them. But again, keep in mind it's more resource intensive. Certainly uses a more advanced algorithm, but it is creating more constraint equations to enforce, the contact condition, and hence it takes a lot more time to solve. But since it converges faster, there could be a trade-off between using this option and the node to surface option. One of the powerful tools that helps to aid in the contact definition is what's called as the contact visualization plot. It not only helps to quickly inspect all of the contact, but allows to also identify unconstrained geometry. Now the contact types are color coded for easy detection. As you can see in this image over here, I have bonded contact, no penetration contact, and allow penetration, are all color coded differently depending upon the contact type. Now there's both geometric based contacts as well as solver based contact. Solver based contacts really helps to identify areas where mesh refinement might be necessary. Geometry-based contact renders the touching geometric entities, edges, faces, or bodies between the different components participating in the contact definition. So for example, I have a two-part assembly here. I might have selected just the touching surfaces for the contact definition, and the geometry-based contact uh, identifies a common edge between those touching geometric entities. However, when I actually look at the same contact definition by running the solver-based contacts, it actually renders the areas of contact at the mesh element level detected by the solver before starting the analysis. So you can see that the solver-based contact detection is totally different from the geometry-based. It actually shows us the projected area of interest that's going to be used for calculation purposes. The contact visualization works really well for both compatible as well as incompatible meshes. So here is a quick illustration of what happens when you have global contact and in both compatible as well as incompatible mesh. How the geometry as well as the mesh or the solver based contact will actually look like. This is really, really useful, especially when you have geometries of mixed types like a beam body, shell body, or just a regular solid body, all interacting through contact definition, whether bonded or no penetration. So it's a great way to identify if your beam is really actually connected to the solid face or the shelf face or not. So let's take a quick look. I'm going to actually go ahead and use this assembly model to illustrate the contact visualization. So I'm going to start off with a simulation setup. So let's look at the mesh real quick. So the mesh is kind of the default mesh setting. It doesn't look real bad. Uh, and I have a few contact sets defined. I have a global contact, I have a component contact, and then I have some local no penetration contacts defined. Now, if I go ahead and look at the contact visualization, simply calculate, it shows me what are the different contacts that has been defined by the user. So here I have a contact between the knuckle and the caliper pieces. I have another contact at the top between the same two parts, and then I have a global contact. Now, under global contact, you can see that it literally goes ahead and shows us all the contact pairs that are participating in this global contact definition. So it's a great way to identify if we have all the contacts taken care of or not. Now, what happens is when I go ahead and check this box that says include solver-based contacts, hit calculate, it actually comes back and says the same contact definition between the knuckle and the caliper. It doesn't, it actually goes ahead and shows me what's going on. So this is the manual contact. If I scroll down the list or just simply uncheck the geometry based contact, now I can clearly see that the no penetration contact detected by the solver is not, it's not looking so great. So this is actually telling me the mesh is actually very coarse in the contact areas, and therefore I need to probably refine the mesh on the geometric entities participating in the contact definition. So let's switch to a simulation setup where I have already done that. So I have a mesh control that is now defined on the areas of contact. And here's what the new mesh actually looks like. So you can see the mesh is a lot more finer on the contact areas if I rotate the model on this side as well. So let's go ahead and run the contact visualization one more time. And let's do a solver-based contact. Click on calculate. There you go. So now you can see that the solver-based contact does a much better job just because of the mesh refinement we applied. And so that's the whole idea of actually using the solver-based contact, is to not only verify if there is a contact between the touching faces of two different parts, as if we have taken care of that, but it also allows for us to actually understand if there is the mesh is adequate in the contact areas, or do I need to actually define the mesh in those contact areas. So it's a great visualization tool, but it's a great troubleshooting tool, especially with respect to contact definitions. All right, so let's talk a little bit about gap in contacts. What are the different options available? In the simulation study properties, there are some common settings with respect to the contact definition. The first one is including global friction. Now, if you have this option checked and a value specified for the friction coefficient, and then you have a global contact set to no penetration, all of the contact sets defined automatically behind the scenes will have this friction value activated at the specified value. Now, keep in mind that this does not automatically activate the friction on manually defined local contact sets. This option for friction must still be specified in your local contact definition as shown here. In most problems, selecting friction in the local contact definition makes the most sense rather than turning on the friction at the global level. Next, the second option in the simulation study properties is called ignore clearance for surface contact. Now what this does is it uses a node to surface or a surface to surface type of formulation. The second option is called ignore clearance for surface contact. This is available both at the global level in the study properties as well as in the local contact definition. Oftentimes you might have geometric entities with an intentional clearance, and so checking this box will ensure that those geometric entities do not come any closer than the clearance, but they can actually move away from each other during the deformation process. Now this option is used with node to surface or surface to surface contact only, and typically it should be turned off for most applications, especially with where you have faces with large curvature differences. So the intended use is to have this option checked in special cases where you have tolerance gaps between touching faces. So when the option is off or not checked, the initial contact is actually assumed if the initial gap is less than or equal to 0.5% of the global element size. When it's on, the initial contact is assumed regardless of the initial gap between faces, and so the initial gaps will be actually ignored during the contact iterations. Incompatible meshes are likely when there is a small clearance between faces of similar curvature. So if the mesh positioning causes numerical penetration, it should be within the tolerance stated above. However, if the convergence fails, retry with this option on. The last one is improving accuracy for no penetration contacting surface, which actually results in the solver slowing down a little bit due to the fact that it's solving more constrained equations to enforce that no penetration contact. So this type of method is referred to as a mortar contact in the literature. It produces a more continuous and more accurate stress with the option checked, and it's really used when defining contact between faces or between a face and an edge. Bottom line is it actually assures robust convergence, but may take a little bit more time to solve. So again, my recommendation is to have this option checked when you have no penetration contact, especially with the surface-to-surface mathematical formulation. You want to make sure that you want to get the most realistic, most accurate results in terms of how the load and the contact area changes between two geometric entities that might be touching each other or moving away from each other. Linear versus nonlinear contacts. The basic contact in a static study defaults to a linear algorithm where certain assumptions are actually made to improve the solution speed. Some of those assumptions are there are no gaps or the gaps are really small between contacting parts. There's little or no sliding action going on. The external load applied is parallel to the contact element, and the faces that touch stay in contact during the deformation process. So if you have a scenario where the loading is not normal to the contacting surface, you can expect some shearing or bending action going on. And so the linear algorithm might still run to completion. However, the results might be totally unrealistic. So if any of the linear conditions are violated, the large displacement option in the study properties needs to be turned on and the problem rerun to get more accurate results. Like I said earlier, if the large displacement option is not turned on, the linear solution may still complete without any warning messages. This doesn't mean the solution is accurate or correct. Now, if you do end up selecting the large displacement option, make sure that at the global level as well as in the local contact definition level, the node-to-node option is not used. The solution with large displacement does take a little bit longer to solve just because of the fact that the external load is now incrementally applied as a function of a pseudo time step. The reason why that's done is because the program continuously updates the overall changing stiffness of the structure during the deformation process. So it actually needs to apply or increment the load intensity in stepwise fashion to make sure that it's able to calculate the changing stiffness of the system in order to get a better, more realistic, more accurate results. All right, to wrap up things, here are some other contact tips. Use split lines to reduce the source area because that can always improve the solution efficiency. Now, if you use split lines in the target area, most likely it's not going to have any effect on the solution. Now, in general, a more refined mesh on the contact faces will certainly result in a better and a faster converging contact. Now, too fine a mesh on the target face could actually end up causing convergence issues. So again, keep in mind, the focus of mesh refinement should be as much as possible on the source geometric entities, not really on the target entities. So in summary, in today's presentation, we explored the in and outs of contact set definition. The capabilities and limitations of each option were reviewed. There were certain recommendations made for contact set choices, and the benefits of large displacement and nonlinear options were actually reviewed. Now, for more information about today's presentation and also to learn more about contact modeling in SOLIDWORKS simulation, make sure you contact your local SOLIDWORKS reseller for a more in-depth training or support on these on using contact conditions in your design work. You can also review the online help for a more detailed description of the features discussed today.
All right, so that concludes this presentation. Stay tuned for more or similar presentations on the Simulation YouTube channel. I'll see you next time. Thanks and have a great day.